Hello, I'm Eliza Tabachnik, and today I'll be walking through my research on evaluating the sustainability of Ethereum scaling mechanisms. Ethereum is a cryptocurrency much like Bitcoin. It consists of a blockchain, which is a database that stores blocks chained together in chronological order. Coins can be traced back to their creation because the relevant data is publicly available. This transparency ensures security by preventing coins being spent twice or created out of thin air. When an error occurs on the blockchain, a consensus mechanism called proof of work is used, where miners can vote to correct mistakes. Many believe that cryptocurrencies are the future of economies. However, Ethereum is increasingly energy-intensive and centralized, directly compromising their founding principles of decentralization and equitable access. In my project, we estimated the energy consumption of Ethereum mining last year at approximately 360.5 billion megajoules, which could power between 1.9 and 3.8 million American households for a year. As you can see on the slide, Bitcoin's energy consumption is greater than Argentina, a country whose population is approaching 45 million. Ethereum's energy use is approximately 1/4 of Bitcoin's, but demand is increasing rapidly. To address this increasing demand, the Ethereum community is currently developing Ethereum 2.0 for 2022, using scaling mechanisms, which are processes implemented on a blockchain to support a higher demand. But the consideration of scaling mechanisms places limited weight on sustainability. The scalability trilemma is the hypothesized impossibility of simultaneously maintaining security, scalability, and decentralization. Ethereum developers aim to overcome this in Ethereum 2.0 by combining scaling and consensus mechanisms with various benefits. We aim to address the flaws in the scalability trilemma and to highlight the importance of explicitly considering sustainability as a factor in what should be the scalability quadrilemma, with estimates of the relative power consumption of each proposed design. Consensus mechanisms are used where participants need to come to an agreement over a blockchain error. As shown in the diagram on the slide, when a fork occurs on the blockchain, in both proof of work and proof of stake, consensus is reached based on the longest chain. So in this instance, the top chain is committed to the blockchain. These two consensus mechanisms have different criteria for ensuring non-fraudulent block is committed to the ledger, which fundamentally impacts the sustainability of the cryptocurrency. When Ethereum's current consensus mechanism, proof of work, is used, the right to update the blockchain is dependent on computing power, which directly results in extreme energy usage. Proof of stake is a newer consensus mechanism where a committee of validators are chosen based on Ethereum currency staked by the participants. Since no specialized hardware is required, this consensus mechanism is more accessible and thus decentralized. This makes proof of stake considerably less energy intensive than proof of work. The scaling mechanisms being considered by Ethereum include zero-knowledge and optimistic rollups, as well as sharding. Rollups are transaction aggregations which reduce the amount of data being uploaded onto the main Ethereum blockchain. Zero-knowledge rollups maintain security through use of zk-SNARK proofs, and in Ethereum will support about 3,800 rollups per second, making them fast. Optimistic rollups do not validate transaction data by default, compromising security. They may be challenged within a dispute time delay of about 1 week, making transaction confirmation slow and impractical. Sharding is where 64 new chains are created to spread the network's load by operating in parallel. This supports a higher demand and thus rapid scaling. Given the early stage of development of these scaling mechanisms, little is known about the environmental impact of each one, which is what we hope to address. We use data from the last year found on Ethereum blockchain BigQuery database maintained by Google. This dataset is updated with the most recent transaction data as soon as a block is uploaded onto the blockchain. Using this data, we simulate the power consumption of the scaling mechanisms combined with both proof of work and proof of stake. Based on this historic data, given that energy is equal to the product of power and time, we simulated the time taken for the computationally intense parts of each process and multiplied that value by the power of the hardware used. For example, simulating zero-knowledge rollups involved estimating the number of blocks mined per second by dividing the average number of transactions per block, which is 186 in our dataset, by the number of transactions per second of each consensus mechanism, which we proved to be 100,000 for proof of stake, and from the BigQuery dataset we know is 14 for proof of work. We then estimated the number of aggregators using the equation on the slide. The major sources of algorithmic computational expense of ZK snarks is modular exponentiation, Groth proofs, and pairing operations, resulting in what we estimated to be 2 seconds per rollup, with an approximation of 55 transactions per rollup. From the dataset, we worked out that the total number of transactions was approximately 440 million, and that the total number of blocks was more or less 2.38 million. Thus, using the block rate estimations from the last slide, we calculated the number of aggregators required. By calculating the product of the results from the previous slides and the total number of blocks, we estimated the time taken. Given that energy is the product of power and time, we substituted in the power consumption of the relevant hardware to estimate the energy consumption of zero-knowledge rollups, if they had been used on Ethereum over the last year. We used a similar method for the other scaling mechanisms, with slight variations. As shown in the first row of our full factorial results table, based on historic data, the average power consumption of proof of work last year was nearly 97 million times more than would have been the case if proof of stake had been used, making a case for proof of stake to be used over proof of work. Optimistic rollups appear to be better for the environment than zero-knowledge rollups when paired with proof of stake, given that they're 1,000 times more efficient and consume 33 watts less power, which is enough to power a light bulb. Sharding, the purpose of which being solely to scale, has a large average power consumption, so on the surface it seems like a poor choice. However, sharding improves the energy per transaction of proof of stake by a factor of 64. Proof of work's high energy consumption per transaction in comparison to proof of stake makes it a highly unsustainable scaling mechanism, because as congestion on the Ethereum network increases, this difference will be magnified. As you can see from this log graph, every scaling mechanism uses less power and has more efficient transactions when paired with proof of stake, making a good case from a sustainability perspective for proof of stake to be used over proof of work. Although zero-knowledge rollups are more energy intensive than optimistic rollups, they're also considerably faster and more secure. Given this, we suggest that zero-knowledge rollups should be implemented in the place of optimistic rollups. As shown in this log graph, one can see that the number of transactions is increasing in a polynomial manner, portraying the increasing popularity of the Ethereum network and the need to scale. This highlights the importance of implementing an efficient scaling mechanism, such as sharding, which, despite its power-intensive nature, given that it uses the most amount of energy of all the scaling mechanisms, is 64 times more efficient than proof of stake, making it ideal for a network with increasing demand. Currently, cryptocurrencies prioritize security, scalability, and decentralization over sustainability. We suggest that sustainability be considered an equally significant factor, as it has real-world consequences from melting glaciers to forest fires. We implore the Ethereum developers to consider the sustainability of scaling mechanisms when developing Ethereum 2.0 by implementing zero-knowledge rollups, proof of stake, and sharding. We hope that Ethereum and other cryptocurrencies looking to scale adopt our recommendations and use our estimates to incorporate sustainability as a factor when scaling. In the future, this research can be extended and developed to simulate other scaling mechanisms and investigate how these processes would interact if certain combinations were implemented on the Ethereum network with respect to power consumption. To strengthen sustainability estimates, data on mempools could be used to predict the estimated increase in demand on the Ethereum network. New variables can be estimated from the prediction data that will be more applicable to the state of the network when these scaling mechanisms are implemented. Thank you so much to my amazing mentor for helping me with this project, and to the other research mentors in my lab group for giving me a fresh perspective on my project. Of course, I'm super grateful to all the research course staff for walking me through the research process as well. Here are my references. Thank you for listening.